We're now going to look at constrained optimization. Now what that means is we've got some function that we're trying to maximize. So say we can write this as f of x, y, z is maximum or minimum subject to some constraint, usually written as g of x, y, z equals 0. So for example, this might mean finding the maximum temperature subject to, say, being on the surface of a sphere, where x squared plus y squared plus z squared equals whatever the radius of your sphere happens to be. So the way we set this up, we use the method of Lagrange multipliers. And the method of Lagrange multipliers says if we want to maximize this function f, we're going to set the gradient of f equal to lambda times the gradient of g, and this will give us a set of the number of equations equal to the number of variables we have, plus the extra constraint equation. So let's look at an example of this. Let's say we wanted to maximize this function x, y squared, z, subject to the constraint that say we're on the surface of a sphere, x squared plus y squared plus z squared equals 9. So we're on the sphere of radius 3, and we want to find the maximum value of this function right here. Well, what we'll do is we'll set up our Lagrange multiplier. We'll take the gradient of f, so we want the gradient of x, y squared, z, and we'll set this equal to lambda times the gradient of this g function over here, x squared plus y squared plus z squared minus 9. So we write out our three components. The partial with respect to x is y squared z, and that on the right hand side the partial with respect to x is 2x times the lambda, so 2 lambda x. If we take our partial with respect to y, on the left hand side we've got 2xyz. On the right hand side we've got 2y times our lambda is 2 lambda y. And then the partial with respect to z is xy squared, and the partial with respect to z on the right hand side is 2z times the lambda, so 2 lambda z. So these are the three equations we get from our gradient, and we also have this fourth equation that's our constraint, that x squared plus y squared plus z squared equals 9. Okay, so now we have 4 equations here, 1, 2, 3, and 4, and 4 unknowns. The unknowns are x, y, z, and lambda. So for starters, looks like we may have to do a fair amount of algebra on this. Before we really get going, I'm just going to look at 2 cases here. First, lambda could be 0, or lambda might not be 0. So if lambda were 0, that would mean this first equation, lambda is 0, that means either y is 0 or z is 0. If that's the case, the entire function is 0. So if lambda is 0, then I know that's going to force my hand and make this function equal to 0. Otherwise, if lambda is not 0, then we're free to divide by it, and that's going to be convenient, as we'll see. So case 1, we've kind of dealt with that. We'll come back to that in case it's our maximum. It probably won't be, but just in case it is, we'll just denote this at the end, in a special case that lambda is 0. So we'll assume for the rest of the work throughout here that lambda is not 0, so we can freely divide it out. So I want to rewrite each of these equations so maybe they're comparable to one another. So let's multiply the first equation by 2x, multiply the second equation by y, and multiply the third equation by 2z. That way, if we look at the left-hand sides, they'll all be 2xy squared z. So that lets us rewrite our first equation as 2xy squared z equals, on the right-hand side, 2 lambda x squared. We do the same on the second equation. We've got 2xy squared z equals 2 lambda y squared. I'm sorry, this first one should be a 4, not a 2, because we distributed the 2 through there. And our third equation becomes 2xy squared z equals 4 lambda z squared. Now since the left-hand sides are all equal, I know the right-hand sides must be equal too. So let's just look at these one at a time. If we take this first equation, we set those two equal to each other. So 4 lambda x squared equals 2 lambda y squared. Now we're assuming that lambda is non-zero, so we can divide it out. So we divide both sides by 2 lambda, and this says 2x squared equals y squared. So that means y must be plus or minus radical 2x. Okay. Doesn't say anything for certain, although it narrows things down a little bit. Let's now look at the first and third equations together. So we know that 4 lambda x squared is 4 lambda z squared. And again, because we're in the case where the lambda is not equal to 0, we can divide it out, and we get x squared equals z squared. And this tells us that z is plus or minus x. So this actually characterizes all of our possible critical numbers on here. It says that we've got an x coordinate, and then we've got our y coordinate, which is plus or minus radical 2x, and then we've got our z coordinate, which is plus or minus x. So we've used up these three equations right here. Now let's plug our critical number into the constraint. So let's plug this into our constraint equation. We've got x squared plus 2x squared plus x squared equals 9. We go and combine these together, and this says 4x squared is 9. We take square roots and solve for x, and we get x has got to be 3 over 2. Plus or minus 3 over 2. So if we plug this back into the point we have so far, this gives us actually 8 separate critical points. We've got plus or minus 3 over 2, that's our x value. Now the sign of the y coordinate, I'm going to use this plus or minus sign, although this plus or minus sign may be different. It's independent of this plus or minus sign. So we actually have two choices of sign in the first term, and then two independent choices on the second component, and these two independent choices on the third component. So we actually have 8 critical numbers here of the various combinations of signs. So we've got our 8 critical numbers. Now we need to test which one of those is actually the maximum. So what we'll do is plug each of those into our original function, and let me just copy down the original. The original was x y squared z. So f of x, y, z was x y squared z. So let's plug each of these points into the function and see which one's the biggest. So we've got 3 over 2, 3 over 2 radical 2, and 3 over 2. Right, and these are all positive numbers. Now if we plug these in, we've got 3 halves for x. We've got 9 fourths times 2 for the y, and then 3 halves for the z. We multiply these out. We multiply all the tops together. We've got 81. We multiply the bottoms together, and we've got 8. So this gives us 81 over 8. So I'm going to come back and look at the other critical points in a second. I want to look back at these cases we'd mentioned before. We said case 1 was where lambda was 0. Case 2 is where it wasn't. So we'd noted that in the case that lambda was 0, the function was 0. Now that could have been a maximum, although now we've tested one of our critical numbers and it was bigger than 0. So we know that case 1, where lambda was 0, this actually was not a max. Occasionally, very rarely, but occasionally that case actually is important and it will be your maximum or your minimum. On this problem it isn't, but it's worth noting. So now let's check the other 7 critical numbers, some critical points. And these are going to be the same numeric values, although we're just going to alter the signs. So I'm just going to shorthand this. Write this as f of positive 3 over 2, positive 3 over 2 radical 2, and negative 3 over 2. And all this is going to do, the numbers are going to be the same, but the signs may be different. So if just the z is negative, when we multiply these out, we're going to get negative 81 over 8. If we look, so we've done the first 2 critical numbers. We've got 6 more to go. If we look at plus minus plus, now here the y is negative. If I square a negative, that's positive. So I get positive 81 over 8. If we change the back 2 signs to negative, Well, we have y being squared, and negative squared is positive, times a negative will give us a negative 81 over 8. So 4 down, 4 to go. Let's look at negative for the x-coordinate. If x is negative, but everything else is positive, this will give us a negative 81 over 8. If we look at f of the x and the z being negative, well, x and z are negative, those negatives will cancel to give us a positive 81 over 8. If we look at f of negative, negative, positive, here the x is negative and the y is negative. Well, y is being squared, so times another negative will give us a negative 81 over 8. We look at f of negative, negative, negative. This is our last one. We've tested all eight critical numbers at this point. If everything is negative, all the negatives wind up canceling and we get positive 81 over 8. So it looks like we have some ties here for the maximum. So this gave us a maximum, as did this one, as did f of the two negatives, the positive in the middle, and f of all three negatives. So we actually have our maximum value is 81 over 8, and the points at which that happens, that occurs at 3 over 2, radical 2, 3 over 2, 3 over 2. That was our first critical point. It also happens at 3 over 2, negative radical 2, 3 over 2, 3 over 2. Right, that was this the second maximum in here, 81 over 8. It also happens down here where we've got negative 3 over 2, positive radical 2, 3 over 2, and negative 3 over 2. And finally, this last critical point, it happens when all three are negative. Negative 3 over 2, negative 2, negative radical 2, 3 over 2, and negative 3 over 2. So these are the 4 points at which it attained its maximum value. And it's worth noting, it wasn't asked for in this problem, but those other 4 points, those were all tied for the minimum. So we actually found the minimum value and the maximum value at the same time in this problem. It wasn't asked for, but we wound up finding it anyway. Now, this method generalizes to maximizing or minimizing subject to multiple constraints. So you may have a problem where you want to maximize or minimize f of x, y, z subject to several constraints, where you've got maybe g1 of x, y, z equals 0 and g2 of x, y, z equals 0. So this may be maybe we want to find the maximum temperature subject to being on the surface of a sphere and along some plane. So we've got 2 separate constraint equations that must be satisfied simultaneously. We'll go through and do this setup because an example will just take too long. The general setup on here is you set the gradient of f equal to lambda 1 times the gradient of g1 plus lambda 2 times the gradient of g2. And this will give you a system of 5 equations. We have 3 equations from the gradient plus 2 constraints is 5 equations, and there are 5 unknowns, x, y, z, lambda 1, and lambda 2. And this method will obviously generalize to more constraints. If you have a third constraint on here where g3 of x, y, z equals 0, then we'll just go and add a third lambda and the third constraint. And it gives us an extra equation, and it gives us an extra unknown. So you can see that this generalizes to higher constraints. And it also generalizes well to more variables. We just generalize the gradient into higher dimensions. So we just take this vector of partial derivatives, and that's the system of equations that we want to solve to give us our max and our min.